So, Professor Sen Gupta, we have the first question, like, what is the reaction fate when the substrates are water insoluble?
Okay. So this is very interesting. Um, so there are two different classes. So one is if it's a liquid, and this is also something which we're trying to study. If it's like of a liquidy substance, so we could make a solution in nitrile or something, maybe 1% organic solvent, and you could add that, and the reaction actually happens in a heterogeneous manner. Okay, and with such rates, and that is something which we're trying to understand, that the substrates are not very water soluble. Okay, but still the reactions are very fast. Okay, so that's one. And in some cases, when the substrates are very hydrophobic, okay, so then in water it's difficult. But sometimes what we do is we dissolve it in 2 to 3% or maximum 5% acetonitrile, and then add that. And so it's sort of a suspension. But even the suspension, the reaction goes nearly to complete. And this is very nice because the only workup you could do is that you could sort of simply use ethyl acetic to extract your product, and that, and rest everything stays in water. Okay, your peroxycarbon stays in water, complex, whatever it is, it's water soluble. So everything is in water, and it's something you can stick it out very clean. Okay, so that's how we do.
Okay, thank you so much, Professor Sen Gupta. Our next question is, what is the correlation between binding energy and redox potential of ligand?
Okay, binding energy. So how strongly it's attached, and how much the rate of potential. Okay. So what I could tell you is that, maybe I answered it differently with camel cases. In camels, we have so when we have so on the head part of the camel, which is the phenyl ring, we sometimes put substrates, right? So we have nitro group as a substrate. When you have a nitro group, it's the pulls the electron density. Okay, so when you have the pulls the electron density out, the redox potential. When you have more electron donation onto the ring, the electron density. So now this would have some correlation with the strength of the nitrogen iron bond, but we really have not. Okay, but what we have looked at is the electron donation, electron withdrawing effect of those groups versus the redox.
Okay, thank you so much. Our next question is, can you please shed some light on the spin multiplicity of these catalysts?
Yeah. So so this is a very good question. So the iron 3 is a spin 3.5. Okay, and the iron 5 oxo is a spin half sister, which is very close to half. And we had both Sam, Sam is an expert. He did some computation for us, and he looked at both the doublet and the quadruplet surfaces. Okay, and the reaction starts going through a doublet surface, and then there is a spin process. Okay, but typically the spin 3.5 is what we start with, and the iron oxo is a spin half, and the reaction starts and proceeds the first activation, to the intermediate through the doublet surface. And that's and during the rebound, I think there's a crossover, if I remember correctly, but the reaction happens to the doublet surface. Okay, and that's what we learned. That we know.
Okay, thank you so much. Our next question is, what was the purpose of adding sodium carbonate with hydrogen peroxide?
Yeah, so we needed, so you can't, sodium hydrogen peroxide is liquid, right? So you needed a solid version of hydrogen peroxide if you want to do a mechanical, something which is also safe and which is also widely used. So sodium peroxycarbonate was something which we figured was something which is widely used. You find this in a washing powder, and this is reasonably stable. Okay, and so that was the one we used, and we also know that a slightly basic condition, it helps this way. Okay, we have always found a pH of 8 to be very optimal. 8.2 is very optimal. So it sort of gives you, does both the jobs. It gives you a solid form of hydrogen peroxide, as well as slightly raises the pH for the most efficient reaction.
Okay, thank you so much. Our next question is, how economical is the usage of these catalysts for treating tons of plastic waste?
Yeah, so that's a very good question. Okay, yeah, so that's something I think time will tell. I can tell you this. So we don't know this, right? But I can tell you this, that it is not about tons of. what are you going to do with taking tons of polyethylene and converting it to high process? This is going to be a small niche market in which you can take a small amount of it and then you can convert. Now, um, this complex is being, this complex is being scaled up and used in large wastewater remediation by a company called Sudoku. You can check the website. Sudoku is trying to do this in wastewater. That's not volume. Okay. So it's possible that we could come up with a version uh, which is more cheaper to make. Okay, and then we could or a conceptually similar idea. So I look at this is a conceptual idea that we could do this whole thing without any solvent. So that is to me what is the most if there's one message I give it, that is that you can take a polymer and you can do it in a solid phase, using hydrogen peroxide, using same complex, right? Now this complex might still be expensive, but we don't know. When you scale this up and if you can get the activities you wanted, maybe it is going to be. Maybe depending on what kind of application and what is the value of it. Okay. But clearly, I don't have an answer right now for your question.
Okay. So we'll take up one more questions. Can these catalysts be used for functionalization of molecules such as ethane or methane?
Yeah, so that's again a very good question. Currently, no, because as I said to you, that one of the things we have sort of said is that when we calculated what we call the BGEAPOH, we got a value of around 100 kilocalories. That means any CH bond which is 100 kilocalories per more or lower would be an exothermic. Now, unfortunately, both methane is 104 and they're higher. Okay? But that doesn't mean so in the thermodynamic term, it is not possible. But it is possible that we create, we create some pocket inside which allows it to come in, and through proximity affects the reaction rates to be. We could bring down the activation energies by different mechanisms, right? So that's something that we would like to try and work on and modify, but we're still not there.
Okay. Thank you so much, Professor Sen Gupta. So we'll be concluding this talk, and this brings us to the end of today's session. We hope that you all enjoyed this broadcast, and we invite you to view the edited recordings from the past events in the ACS Science Talks library. You'll receive your certificate of participation along with a survey form upon your experience about the ACS Science Talks. So, on behalf of all of us at ACS, thank you for joining us today. We hope to see you again soon for more ACS events. Till then, stay safe and healthy. And thank you again, Professor Sen Gupta, for this wonderful lecture and sharing your insights. Thank you so much.
Thank you very much, Neha and others in ACS, and thank you for giving me the opportunity. It was a
Thank you.
pleasure giving this lecture.
Thank you so much. Thank you so much.